Lie down, settle into the quiet of your surroundings, and let the small noises around you fade into the background. Close your eyes gently, feeling the surface beneath you, the weight of your body grounding you, and let your mind soften, ready to explore a question as vast as the universe itself. Imagine the sensation of floating gently, suspended between thought and observation, as if the air itself carries the quiet hum of unseen processes. In that calm, receptive state, consider a single question. What if everything you perceive as real, the light around you, the sounds, the passage of time, is the product of a structured, deliberate computation? The notion is not new. It has roots in human contemplation, stretching back millennia. Philosophers have long asked whether reality is truly as it seems, or if our senses deceive us. Plato imagined shadows on a wall as the entirety of experience for those confined to a cave, suggesting that perception alone might not capture the full truth. Centuries later, René Descartes proposed a thought experiment in which a powerful, possibly deceptive entity could manipulate our senses, creating an illusory world indistinguishable from reality. These early philosophical inquiries laid the conceptual groundwork for a question that intersects with the edge of modern science. Could our universe itself be a simulation? In contemporary terms, the idea has been formalized by thinkers such as Nick Bostrom, whose simulation hypothesis frames the question in probabilistic, scientific terms. Bostrom suggests that if technologically advanced civilizations eventually possess the capability to run detailed simulations of ancestral experiences, then the number of simulated realities could vastly outnumber the one original base reality. By sheer probability, it becomes plausible, though not certain, that any conscious being, ourselves included, might exist within one of these computationally generated environments. Here, a simulation is not metaphorical, but literal in the sense of being a structured, information-driven reality operating under algorithmic rules. To evaluate this hypothesis, we consider the trajectory of technological development. Computing power has grown exponentially over the past century, with each generation of processors capable of performing calculations at previously unimaginable speeds. Moore's law, the observation that transistor density, and therefore processing capability, doubles approximately every 2 years, has held for decades, suggesting that the computational demands of simulating complex environments may be within reach for sufficiently advanced civilizations. Virtual reality and artificial intelligence are early, partial glimpses into the capacity to create immersive, self-consistent digital worlds, where characters exhibit lifelike behavior and emergent phenomena arise from computational rules. The universe itself presents phenomena that can be examined through the lens of computation. Physical laws operate with remarkable consistency, as though the cosmos runs on defined rules akin to a program. Quantum mechanics introduces fundamental discreteness in energy states and limits on simultaneous measurement reminiscent of quantized variables in digital systems. The Planck scale, the smallest measurable unit of space and time, suggests a natural granularity that some theorists have compared to a digital grid underlying reality. Even the speed of light, the constants of gravity, and the behavior of subatomic particles might be interpreted as parameters within an overarching computational structure, providing a framework in which complex phenomena emerge predictably. Observational science has sought empirical markers that could hint at a simulated structure. Cosmic ray propagation, for instance, reveals energy limits that some scientists have speculated could correspond to the resolution of a lattice-like universe. The holographic principle proposes that three-dimensional space can be encoded on a two-dimensional surface, offering a mathematical structure that resonates with the concept of information-driven reality. While these findings are not evidence of simulation per se, they illustrate that our physical theories accommodate frameworks in which a universe could be represented as an information system, subject to rules and constraints similar to those found in computational models. Consciousness itself becomes a central consideration. If we exist in a simulation, the awareness we experience, the continuous stream of thoughts, sensations, and memories, is generated internally, yet interfaces seamlessly with an environment governed by underlying rules. Neuroscience demonstrates that consciousness arises from complex interactions between neurons and synaptic networks. Analogously, a sufficiently detailed simulation could produce emergent consciousness by replicating or simulating these interactions, blurring the line between a biologically rooted awareness and one produced algorithmically. This perspective reframes questions of free will, choice, and the meaning of observation within a simulated framework, without venturing into speculative narrative. Skepticism remains scientifically warranted. A simulation hypothesis, while logically consistent, faces challenges of falsifiability. Empirical science relies on testable predictions, and proving or disproving simulation conclusively is profoundly difficult. Proposed tests, such as examining the distribution of high-energy cosmic particles or searching for limits in physical constants, have yet to yield conclusive evidence. This ambiguity emphasizes the importance of distinguishing rigorous, observation-based reasoning from metaphysical or philosophical speculation, maintaining a commitment to empirical grounding while exploring conceptual possibilities. The intersection with cosmology further enriches the discussion. Theories of cosmic inflation, multiverse scenarios, and fine-tuned constants intersect with the simulation hypothesis by illustrating the vast landscape of potential realities. If multiple universes exist, each governed by differing parameters, a simulated reality becomes one variant among many possible configurations. The statistical prevalence of such universes, or simulations of them, can influence the likelihood of our own existence as observers in a computationally instantiated framework. Cosmological observation, then, provides a natural context for assessing our universe's structure through both physical law and informational architecture. Future experimental prospects suggest cautious optimism for deepening understanding. Advancements in quantum computing, high-energy physics, and observational astronomy may allow increasingly precise measurements of cosmic structures and interactions. By probing the fabric of space-time at smaller scales or testing the consistency of physical constants, scientists might identify patterns suggestive of computational underpinnings. These investigations do not claim to confirm simulation, but provide rigorous avenues for evaluating the plausibility of information-driven models of reality, anchoring speculative inquiry within empirical methodology. Finally, reflection returns the mind inward. Contemplating the possibility of a simulated universe does not diminish the richness of experience. The perception of colors, the texture of surfaces, the rhythms of thought, and the flow of time retain their intrinsic qualities, whether or not they emerge from computation. Engaging with these ideas can foster a sense of wonder, curiosity, and humility, emphasizing the depth of our observational faculties and the sophistication of the universe, or universe-like systems, in which consciousness emerges. Awareness, regardless of the underlying framework, remains the canvas upon which existence is painted. As your attention gently drifts across these thoughts, notice the calm that accompanies quiet contemplation. Whether or not we inhabit a simulation, the process of observation, questioning, and understanding connects each mind to the structure and mystery of reality. Let the stillness linger, carrying both curiosity and acceptance, as the complexity of the universe, simulated or not, exists around and within every moment you perceive. Beyond the conceptual framework, the structure of the universe itself offers subtle cues that invite scrutiny through the lens of information processing. The cosmic microwave background, a relic radiation from the early universe, presents a nearly uniform field punctuated by slight variations. These fluctuations, measured with increasing precision, reveal the seeds of galaxies, clusters, and vast cosmic filaments. Some physicists have noted that the statistical properties of these variations might be interpreted as data points in a vast computational lattice, though such interpretations remain tentative. Yet, the very possibility encourages examination of whether the patterns we observe are emergent properties of underlying rules, rather than purely random processes. In parallel, quantum phenomena illuminate the relationship between observation and reality in unexpected ways. The act of measurement itself influences outcomes, exemplified in experiments like the double-slit experiment. Particles exist in superpositions, only adopting definite states when interactions occur, a process reminiscent of computational algorithms, rendering details only when required. Entanglement further challenges classical notions of locality and separability, suggesting a form of non-local information structure that could be analogous to data connections within a simulated environment. These phenomena, while grounded in empirical study, inspire reflection on the universe's possible informational architecture. The interplay of physical constants adds further dimension to this inquiry. Constants such as the gravitational constant, the fine structure constant, and the cosmological constant exhibit values that allow for the formation of complex structures, from stars to planetary systems. Small deviations in these constants could preclude the existence of galaxies or stable chemistry. This fine-tuning invites contemplation. If the universe were a simulation, the parameters might be deliberately set to support complex observers capable of reflection and experimentation. Even without invoking intention, the precision and interdependence of these values suggest a system operating under coherent rules, the kind that can be formally described, modeled, and in principle computed. Considering computational limits, one encounters both opportunity and constraint. The ultimate processing capacity of a hypothetical simulation would need to account for the information content of an entire universe, potentially including every particle, field, and emergent process. Yet our understanding of physics provides natural bounds: the Planck length and time, the maximum entropy within a given volume defined by black hole thermodynamics, and the limits imposed by the speed of light, all suggest that a discretized, finite informational structure could, in principle, encode the universe. This notion aligns with some theoretical models of digital physics, in which the universe is described fundamentally in terms of information rather than continuous matter. Observational proposals have emerged to test for these structures. High-energy particle experiments, lattice-based simulations of cosmology, and precise measurement of fundamental constants are among the methods suggested to reveal potential signatures of underlying computation. For instance, if space-time were a discrete lattice, particles at extreme energies might exhibit anisotropies or directional biases in behavior detectable in cosmic ray propagation or gamma-ray bursts. Although no conclusive evidence has yet been found, the conceptual clarity of these proposals illustrates that scientific inquiry can meaningfully engage with questions of simulated reality without leaving empirical grounding. The holographic principle provides another avenue for connecting observation with theoretical possibility. It posits that all information contained within a volume of space can be encoded on its boundary, much like a two-dimensional projection encoding a three-dimensional object. The principle emerges naturally from considerations of black hole entropy and quantum gravity, suggesting that the universe is not only describable in informational terms, but may fundamentally operate as an encoded system. This framework resonates with the simulation hypothesis, as it implies that three-dimensional reality could emerge from underlying informational structures, analogous to the way a digital environment is generated from code. Consciousness within such a system remains a critical focus. If subjective experience arises from patterns of information processing, as suggested by computational theories of mind, then simulated consciousness could be indistinguishable from biological consciousness. Neural networks, both natural and artificial, demonstrate emergent behaviors, learning, and pattern recognition. Extending these principles to a simulated universe suggests that individual awareness might be a product of coherent, rule-governed computation, interacting seamlessly with the simulated environment. The implications are profound. Our sense of self, memory, and perception could all be instantiated within a broader informational substrate, raising questions about identity, continuity, and agency. Philosophical reflection complements scientific inquiry. Accepting the plausibility of a simulated universe challenges assumptions about causality and existence, but does not diminish the richness of lived experience. Ethical and existential considerations arise naturally. If observers are simulated, what responsibilities might creators have towards them? What meaning emerges when one understands that subjective experiences may be algorithmically produced? These questions, while speculative in terms of motivation or purpose, highlight the depth of engagement possible when contemplating the structure and origins of reality through rigorous observation and reasoning. The intersection of cosmology and simulation theory continues to provoke thought. The concept of a multiverse, suggested by inflationary models and string theory landscapes, provides a statistical framework for understanding the prevalence of observer-friendly universes. In this context, a simulated universe could be one among many, selected according to parameters conducive to complexity and consciousness. The fine-tuning of physical constants, the emergence of stable structures, and the prevalence of phenomena conducive to life and observation cohere into a picture in which the universe can be understood both as a natural system and as one that is potentially informationally instantiated. Experiments at the forefront of physics, including high-precision tests of fundamental constants, advanced particle collision studies, and observational cosmology, continue to probe the structure of reality. While the results do not confirm the simulation hypothesis, they refine our understanding of the universe's architecture. Each measurement, each detection of subtle irregularities, contributes to a growing body of knowledge that informs the plausibility of computational explanations. In this sense, the pursuit of scientific understanding and the contemplation of simulation are not opposed. Rather, they are complementary explorations of the same underlying reality. As reflection deepens, attention returns inward. Contemplating a potential simulation frames the human experience in a different light, emphasizing both the fragility and resilience of perception, awareness, and understanding. Every thought, sensation, and observation can be appreciated as an interaction with a consistent, rule-governed environment, whether emergent naturally or generated algorithmically. This perspective nurtures a profound sense of curiosity and presence, highlighting the interconnectedness of knowledge, observation, and existence, and underscoring the beauty inherent in even the most abstract contemplations of reality. Examining the universe through the lens of information reveals subtle patterns that invite further reflection. The cosmic microwave background, a faint glow permeating all of space, carries within it the earliest imprints of the universe's formation. Tiny variations in temperature and density, mapped with exquisite precision, trace the emergence of galaxies and clusters over billions of years. Some scientists suggest that such detailed regularity could be seen as analogous to data points in a computational grid, where emergent structures arise naturally from underlying rules. These observations highlight that even at the largest scales, the universe exhibits coherence and order that can be formally described, measured, and modeled. Quantum mechanics presents additional layers of complexity that intersect intriguingly with the notion of computation. In phenomena such as superposition, particles exist in multiple potential states simultaneously, collapsing into a defined state only upon observation or interaction. Entanglement, in which particles exhibit instantaneous correlations across vast distances, challenges classical intuitions of locality. Such behaviors, consistently confirmed through experiment, demonstrate that the fundamental nature of reality is profoundly relational and information dependent. From the perspective of computational modeling, these properties could be interpreted as efficiencies within a system that only renders outcomes when interaction occurs, minimizing computational load while maintaining coherent outcomes. The fine-tuning of physical constants further emphasizes the structured nature of our reality. Parameters such as the gravitational constant, the electromagnetic coupling, and the cosmological constant exist within extraordinarily narrow ranges that permit the formation of stars, planets, and chemistry capable of supporting life. Slight deviations in these values would dramatically alter the emergence of complex structures. In a simulation framework, this precision could be seen as the establishment of parameters sufficient to sustain observers, a necessity for any system intending to model complex, self-aware entities. Even outside speculative interpretation, the interdependence of constants suggests that the universe operates according to coherent, interrelated rules, measurable and consistent across vast scales. Considering the limits of computation, the universe presents natural boundaries. The Planck scale, representing the smallest measurable units of space and time, introduces a fundamental granularity reminiscent of digital discretization. Black hole thermodynamics, with its association of entropy and surface area, implies an upper bound to information density within a given volume. These principles suggest that a finite, rule-governed system could, in principle, encode the universe, with emergent phenomena unfolding from fundamental informational rules. The parallels between these natural limits and the architecture required for large-scale simulations are striking, even if the existence of such a simulation remains a hypothesis. Empirical exploration of potential simulation indicators has begun in earnest. Researchers have proposed examining cosmic rays at extreme energies for directional biases or anomalies, which could reveal an underlying lattice structure to space-time. Experiments that probe the behavior of fundamental particles and interactions at unprecedented precision also serve to test the coherence of physical laws. While no definitive evidence has been found, the formulation of these experiments demonstrates that questions of computational or informational structures in the universe can be approached scientifically through measurable effects and testable predictions, rather than purely speculative reasoning. The holographic principle provides another avenue for connecting observation with theoretical models of reality. According to this principle, all information contained within a volume of space can be described by data encoded on its boundary. This insight, derived from considerations of black hole entropy and quantum gravity, aligns with the view that our three-dimensional reality may emerge from underlying information structures. Such a framework resonates with the concept of a simulated universe, suggesting that reality can be encoded, processed, and manifested from an informational substrate, much as a virtual environment arises from computational code. The study of consciousness within these frameworks further deepens understanding. Conscious experience arises from complex networks of information processing, as observed in neural networks of the brain. If consciousness is fundamentally computational, then it could emerge within a simulated environment, just as it does biologically. Awareness, memory, and perception may be instantiated through coherent, rule-governed processes interacting seamlessly with the environment, whether that environment is biological or algorithmically constructed. This consideration reframes notions of self, free will, and personal experience within a system governed by computational rules, while remaining grounded in empirical understanding of information and cognition. Philosophical reflection complements these scientific perspectives. Even if the universe were a simulation, the richness of sensory experience, thought, and observation remains intact. Ethical and existential considerations arise naturally, prompting questions about the responsibilities of creators and the significance of subjective experience. These inquiries, while speculative regarding motivation or intent, remain grounded in the observable and measurable reality of consciousness interacting with structured systems. They illustrate that contemplation of simulation can be intellectually rigorous, intersecting with both scientific observation and reasoned philosophical analysis. Cosmology further informs this inquiry. The multiverse concept, suggested by models of cosmic inflation and string theory landscapes, posits a vast ensemble of universes, each with differing physical parameters. In such a scenario, a simulated universe could be one variant among countless possibilities, selected for conditions that permit complexity and observers. Fine-tuning, emergent structures, and the stability of physical laws become statistically significant, enhancing the plausibility that observed coherence is consistent with both natural laws and informationally constrained models. This intersection of cosmology and computation provides a framework for assessing the simulation hypothesis within the context of empirical observation. Scientific investigation continues to probe these ideas with precision. Particle accelerators, gravitational wave detectors, and observational surveys of the cosmos expand understanding of physical laws and structures. Each measurement refines models of the universe, illuminating the coherence, consistency, and limitations of observable phenomena. Whether the universe is naturally emergent or computationally instantiated, the pursuit of knowledge uncovers layers of structure and pattern that inform both scientific theory and philosophical reflection, bridging empirical study and conceptual inquiry in an ongoing dialogue with reality itself. As we continue to examine the universe with precision, patterns of complexity emerge at every scale, revealing an underlying order that resonates with the logic of computation. Galaxies form intricate clusters, gravitationally bound, yet distributed across vast cosmic filaments, while within these galaxies, stars ignite and die in cycles that sustain chemical diversity. Planetary systems coalesce from dust and gas, exhibiting remarkable regularity in orbital mechanics. These processes unfold according to predictable physical laws, yet the emergent complexity appears almost organic, as if a sophisticated program orchestrates countless interactions to produce coherent, self-consistent outcomes. High-energy physics provides another vantage point for exploring the universe's structure. Collisions within particle accelerators recreate conditions present in the earliest moments after the Big Bang, allowing observation of fundamental particles and their interactions. The standard model of particle physics, while incomplete, offers a remarkably accurate description of these interactions, suggesting that the universe's behavior is governed by consistent rules. In some interpretations, these rules could be conceptualized as computational algorithms, processing information to maintain coherence across space, time, and matter. Experiments detecting subtle anomalies or constraints in particle behavior might reveal the architecture of the underlying system, much like debugging data in a complex simulation. At the quantum level, phenomena such as wave function collapse and entanglement further reinforce the notion of information-driven dynamics. Superposition allows particles to exist in multiple states simultaneously, only adopting a specific outcome when interaction occurs. Entanglement produces correlations that defy classical intuition, demonstrating that information can manifest non-locally across the system. These behaviors, empirically verified through repeated experimentation, suggest that the universe operates on principles that prioritize efficiency and coherence, which could be interpreted as computational strategies minimizing resource usage while maintaining emergent order. Cosmic rays and the highest energy particles observable in the universe offer additional clues. Theoretical physicists have proposed that discrete lattice structures in spacetime might impose limits on particle propagation or directionality, producing detectable anisotropies. Observing such patterns could provide indirect evidence of an underlying informational structure. While no conclusive evidence has yet emerged, the very formulation of these tests demonstrates that scientific methodology can engage with the possibility of simulation, relying on measurable effects and reproducible results rather than speculation alone. The holographic principle reinforces this perspective by suggesting that the total information content of a volume of space can be encoded on its boundary, much as a two-dimensional surface might encode a three-dimensional scene. This principle arises naturally from black hole physics and quantum gravity, indicating that reality may be fundamentally informational. If three-dimensional space can emerge from encoded data, the universe can be understood as an information processing system where macroscopic phenomena are emergent properties of underlying rules, much like rendered environments in advanced virtual simulations. Consciousness within such a universe is similarly consistent with information-based models. Neural networks in the brain process information to produce awareness, memory, and perception. If consciousness is computationally instantiated, simulated beings could experience awareness indistinguishable from that of biological entities. This perspective emphasizes that the subjective experience, the continuous sense of self, the perception of time, and the flow of sensations is compatible with a reality structured by information. Even if the universe is computational, the richness of lived experience remains profound, and the internal coherence of perception preserves the authenticity of each moment. Philosophical reflection arises naturally from these considerations. Ethical and existential questions emerge when contemplating the possibility of simulated existence. What responsibilities might creators have toward conscious beings? How does one define meaning and purpose within a system, potentially governed by rules rather than independent causality? These questions do not require speculation about intent, but focus instead on the structure and consequences of observable processes. By grounding reflection in measurable, empirical knowledge, one can explore the implications of simulated reality without departing from rigorous reasoning. Cosmological theories intersect seamlessly with these ideas. The multiverse concept suggests a vast ensemble of universes, each with distinct parameters and laws. Within this framework, a simulated universe could be one variant optimized for complexity and the emergence of observers. The statistical likelihood of inhabiting a universe capable of supporting consciousness is enhanced when considering multiple realizations, providing a natural explanation for fine-tuning without invoking extraordinary coincidence. Observations of cosmic structure, inflationary dynamics, and large-scale matter distribution all contribute to understanding the statistical and physical context of our universe. Empirical exploration remains central to this discourse. Advanced observational programs, including precision cosmology, gravitational wave detection, and particle physics experiments, continually refine our understanding of universal laws. Each discovery provides incremental insight into the consistency, limitations, and emergent properties of reality. By investigating anomalies, patterns, and regularities, scientists approach the question of underlying structure systematically. These efforts exemplify the productive interplay between conceptual hypotheses, such as simulation, and rigorous empirical methodology. demonstrating that contemplation of informational reality can coexist with, and indeed inspire, scientific advancement. Through all of these investigations, a recurring theme emerges. Whether or not the universe is a simulation, its structure is intelligible and accessible to observation, measurement, and reasoning. Patterns manifest across scales, from subatomic interactions to galactic arrangements, forming a cohesive tapestry of phenomena. The emergent complexity of the cosmos, its precise laws, and the consistency of observable interactions collectively suggest that reality operates under coherent principles, whether they are naturally emergent or algorithmically instantiated. Engaging with this complexity fosters a deepened appreciation for the mechanisms that allow consciousness to emerge and perceive them. Finally, attention returns inward to the human observer experiencing this vast system. Contemplating the possibility of a simulated reality encourages introspection, highlighting the remarkable interplay between observation, awareness, and structure. Each thought, sensation, and perception is part of a consistent, intelligible framework, whether naturally evolved or computationally instantiated. Accepting the plausibility of simulation need not induce anxiety or doubt. Rather, it underscores the elegance and subtlety of the universe, offering both intellectual engagement and a sense of calm reflection. By embracing wonder, curiosity, and empirical reasoning, the mind navigates the profound, intricate landscape of reality, finding both insight and serenity in the process. Looking ahead, scientific inquiry continues to push the boundaries of what can be observed, measured, and understood, revealing ever more intricate layers of the universe's structure. High-precision astronomical surveys map the distribution of galaxies across billions of light years, uncovering patterns that suggest an underlying coherence in cosmic architecture. Observations of dark matter and dark energy, though their nature remains elusive, point to pervasive influences shaping large-scale structure. Each measured anomaly, gradient, and alignment invites careful analysis, offering opportunities to examine whether the consistency of physical laws reflects emergent natural order or hints at an informational framework capable of sustaining complex phenomena. Simultaneously, advances in particle physics deepen understanding of fundamental constituents of reality. Experiments at accelerators probe interactions among quarks, leptons, and bosons, revealing the Standard Model's remarkable predictive power. The discovery of the Higgs boson confirmed mechanisms governing mass and symmetry breaking, while ongoing research investigates phenomena beyond the Standard Model, including neutrino oscillations, supersymmetry, and potential hidden dimensions. Each discovery expands the dataset with which theoretical physicists can test the limits of physical law. Within the simulation hypothesis, such findings could be interpreted as the exploration of system parameters, revealing the underlying code that dictates observed behavior. Quantum information theory provides additional insight into the nature of reality as potentially computational. Concepts such as quantum entanglement, decoherence, and error correction illustrate that information at the fundamental level behaves according to precise mathematical rules. The universe exhibits self-consistent correlations across scales and systems, allowing predictions and modeling that, while probabilistic, remain reliable. This observation aligns with the idea that reality might operate as a structured informational system, capable of propagating coherent interactions while minimizing inconsistencies, an efficiency analogous to principles used in sophisticated computational simulations. Cosmological investigations also examine fine-tuning and the emergence of complexity. The formation of stars and planets follows predictable sequences shaped by gravity, thermodynamics, and chemical processes, giving rise to environments suitable for life. The anthropic principle suggests that observers naturally find themselves in regions of the universe compatible with their existence. When considered alongside simulation hypotheses, these observations underscore a statistical perspective. Universes or systems capable of sustaining consciousness will necessarily exhibit parameters conducive to complexity, whether through natural selection, cosmic variance, or intentional design within computational frameworks. Observational tests continue to be proposed for detecting potential signatures of simulation. Lattice-based models of spacetime suggest that at extremely small scales, discretization could produce detectable anomalies in particle behavior. Searches for violations of Lorentz invariance, directional biases in high-energy particle flux, or unexpected deviations in cosmological background radiation offer possible empirical avenues. Although none have yet revealed definitive evidence, the rigor of these proposals demonstrates that simulation can be explored scientifically. The approach emphasizes testability, measurement, and falsification, maintaining adherence to the empirical methods that define modern physics. The holographic principle remains central to theoretical discussions, providing a compelling framework in which three-dimensional phenomena emerge from two-dimensional informational substrates. Black hole, thermodynamics, and quantum gravity offer supporting mathematical structures, illustrating that the universe may fundamentally encode information in ways that parallel the architecture of advanced computational systems. This principle suggests that macroscopic coherence, the stability of physical laws, and the emergence of complex structures may all arise from an underlying information-rich substrate, offering a conceptual bridge between physical observation and informational modeling. Consciousness continues to offer fertile ground for exploration. The brain's intricate networks of neurons process and integrate information, producing subjective experience, memory, and perception. Computational models of cognition demonstrate that coherent information processing can give rise to emergent behavior. Extrapolating these principles, simulated consciousness could, in theory, mirror biological awareness, experiencing continuity, self-reflection, and perception without distinction from biological life. This perspective reframes philosophical questions about the self and free will, while remaining consistent with empirical studies of information processing, neurobiology, and cognition. Philosophical implications extend into reflections on meaning and ethical responsibility. Even if our reality is computationally instantiated, the richness of perception, thought, and interaction retains significance. Ethical questions emerge regarding the treatment of conscious systems and the consequences of observation. Observers within a potentially simulated universe must reconcile the experience of agency with the possibility of underlying structure, balancing curiosity with acceptance. These considerations emphasize that engagement with the simulation hypothesis can be intellectually rigorous and personally meaningful without requiring metaphysical speculation about creators or ultimate purpose, cosmological perspectives complement these philosophical reflections. The multiverse framework, informed by inflationary theory and string landscape models, posits vast ensembles of possible universes, each with distinct laws and parameters. Within this context, the universe observed by conscious beings may naturally arise as a statistically favorable environment for complexity. Simulation could be interpreted as a mechanism for exploring or reproducing such environments, with emergent observers arising as part of the system's coherent dynamics. Observational evidence from cosmic structure, matter distribution, and the isotropy of radiation all reinforce the impression of consistent, law-governed phenomena, whether emergent or instantiated computationally. Ultimately, the pursuit of understanding engages both empirical observation and contemplative reflection. Scientific investigations, from particle collisions to deep space surveys, reveal layers of order, constraint, and complexity. At the same time, consideration of consciousness, emergent complexity, and informational structure allows insight into the profound subtlety of reality. Whether the universe operates naturally, computationally, or through some combination thereof, the patterns and structures we observe testify to a system of remarkable coherence. Engaging with these patterns nurtures both intellectual curiosity and a contemplative calm, highlighting the beauty and intricacy of the cosmos as experienced by aware observers. Advancements in observational technology continue to sharpen our understanding of the universe's intricate patterns. Telescopes surveying the cosmos at multiple wavelengths, from radio waves to gamma rays, uncover structures that reveal both vast regularity and subtle anomalies. The distribution of galaxies along cosmic filaments, the dynamics of galaxy clusters, and the behavior of dark matter all provide insights into how matter organizes under fundamental forces. Each observation reinforces the notion that universal processes follow coherent, measurable rules. In the context of a potential simulation, these processes can be interpreted as algorithmically governed interactions, where large-scale order emerges from consistent, underlying principles. High-energy astrophysics offers another lens through which the informational nature of reality might be investigated. Cosmic rays, neutrinos, and gamma-ray bursts carry information about the most extreme conditions in the universe, often tracing events billions of years old. Some theoretical models suggest that discrete features in these energetic phenomena could indicate a finite, lattice-like structure of space-time. Although no definitive evidence of such discretization has been observed, the formulation of these hypotheses demonstrates that the simulation hypothesis is approachable through empirical study. Precision measurements at these extreme scales challenge both theoretical models and observational techniques, reinforcing the interplay between scientific rigor and conceptual exploration. Simultaneously, quantum mechanics continues to illuminate how information underpins fundamental processes. Experiments demonstrating superposition, entanglement, and decoherence reveal that the state of a system often exists in a spectrum of possibilities until measured or interacted with. These behaviors, consistently reproducible, indicate that reality operates on probabilistic yet rule-based principles. From a computational perspective, such phenomena resemble on-demand rendering. Outcomes are instantiated as needed, maintaining coherence across the system while optimizing efficiency. The analogy underscores that the universe's operations can be described both mathematically and conceptually in terms of information processing, without invoking speculative narrative. Cosmic fine-tuning remains a striking feature. Constants governing gravity, electromagnetism, and nuclear interactions occupy ranges that allow for stable stars, planetary formation, and chemistry capable of supporting life. Minor deviations in these parameters would yield drastically different universes, often incapable of sustaining complexity. Whether this tuning arises naturally through physical law, selection across a multiverse, or as part of a computational framework, the result is a universe structured to permit intricate interactions and the emergence of observers. The regularity and interdependence of these constants reinforce the perception of a coherent, finely structured system, whether naturally emergent or algorithmically constrained. Consciousness continues to illuminate the discussion from within. Neural networks in the human brain demonstrate that emergent awareness arises from highly organized information processing. Memories, perception, and decision-making emerge from complex interactions among neurons, producing coherent, subjective experience. If consciousness is computationally instantiated, simulated awareness could mirror these properties, experiencing continuity, perception, and reflection without distinction from biological consciousness. This notion emphasizes that the observer's experience retains authenticity and significance, regardless of the underlying nature of the system generating it. Philosophical reflection complements empirical study. Contemplating the possibility of a simulated reality invites consideration of meaning, ethics, and human perspective. Ethical questions arise regarding the responsibilities of potential creators toward conscious entities, while existential questions explore the significance of agency, purpose, and observation. Importantly, these reflections need not rely on speculation about intent. They are grounded in observable properties of consciousness, structure, and complexity. By integrating scientific understanding with philosophical insight, a richer perspective emerges, connecting observation, reasoning, and awareness in a unified contemplation of reality. The multiverse framework further contextualizes simulation possibilities. Inflationary models and string theory suggest the existence of numerous universes, each with differing laws and constants. Within this framework, the statistical likelihood of inhabiting a universe capable of supporting complex observers is increased. Simulation, in this context, could represent one mechanism among many for realizing universes with coherent structure and emergent complexity. Observations of large-scale matter distribution, radiation isotropy, and cosmic evolution reinforce the perception of a system governed by consistent, measurable principles, whether emergent or computationally instantiated. Scientific methodology remains central to advancing these ideas. Experiments ranging from particle accelerators to gravitational wave detection and deep sky surveys expand empirical knowledge. Each measurement refines theoretical models, illuminates constraints, and identifies patterns across scales. Anomalies provide opportunities to test assumptions, while reproducible results establish robust understanding. By engaging with the universe through measurement, calculation, and observation, the interplay between conceptual frameworks like the simulation hypothesis and empirical science becomes tangible, demonstrating that even abstract notions can be approached rigorously without abandoning factual grounding. reflection on human perception and awareness brings the narrative inward once more. Every sensation, thought, and observation occurs within a consistent, rule-governed framework, whether naturally emergent or computationally instantiated. The coherence of experience, the reliability of physical laws, and the richness of emergent phenomena provide both insight and reassurance. By contemplating the intricate structure of reality, observers can appreciate the elegance of the universe, the precision of its rules, and the subtle interconnection of phenomena across scales. This awareness fosters both intellectual curiosity and calm reflection, merging empirical understanding with the experiential dimension of consciousness. As we contemplate the universe further, attention turns to the emergent phenomena arising from the interaction of fundamental laws. From the coalescence of hydrogen and helium into the first stars to the formation of complex chemical systems on nascent planets, structures arise through iterative, rule-governed processes. Stellar nucleosynthesis produces the elements necessary for planets, life, and consciousness itself, illustrating how local interactions under consistent physical laws yield outcomes of remarkable complexity. These emergent patterns, predictable in principle, yet intricate in manifestation, suggest that the universe operates according to coherent principles capable of producing vast diversity from simple rules. The study of planetary systems highlights another dimension of this order. Orbital mechanics, dictated by gravitational interactions, generates stable environments conducive to long-term evolution. The balance between orbital eccentricity, stellar luminosity, and planetary composition influences climate stability and chemical diversity. Such constraints echo the broader theme of fine-tuning. Subtle variations can produce drastically different outcomes, reinforcing the impression of a structured system in which complexity and observation can arise. These processes, observable across the galaxy, demonstrate the universality of physical law and the potential for systematic patterns to manifest repeatedly. At the microscopic scale, quantum mechanics continues to provide insight into how complexity emerges from probabilistic rules. Atomic and molecular interactions are governed by discrete energy states, selection rules, and entanglement phenomena. Chemical reactions, catalysis, and molecular assembly all rely on these predictable principles, yet the combinations and interactions produce immense diversity in material and biological systems. In this context, the universe behaves like an intricate computational system where local rules generate globally coherent and remarkably intricate structures, allowing for the emergence of complex phenomena, including life and consciousness. Technological progress provides a complementary perspective on these principles. Advancements in computational modeling, quantum simulation, and artificial intelligence allow humans to emulate, in part, the processes that govern natural complexity. Simulations of stellar evolution, galactic formation, and molecular dynamics reveal that simple rules, iteratively applied, produce outcomes mirroring observed reality. The capacity to model these phenomena with increasing fidelity emphasizes that complexity can emerge from structured processes, whether in natural systems or within designed computational frameworks. This insight bridges empirical observation with conceptual reflection on the nature of reality itself. Emergent complexity is also evident in biological systems. Life arises from chemical interactions, that obey physical and chemical laws yet exhibit self-organization, adaptation, and evolution. Genetic information encodes instructions that, when expressed, produce organisms capable of responding to their environment, reproducing and generating further complexity. These processes exemplify how rule-governed interactions at one scale give rise to intricate structures and behaviors at higher levels, illustrating a hierarchy of emergent phenomena that aligns with both natural and computational models of system evolution. Observational tests continue to probe the universe for subtle indicators of underlying structure. High-precision measurements of cosmic radiation, particle interactions, and gravitational phenomena refine models of space-time and physical law. The search for anomalies, discreteness, or non-random patterns provides opportunities to assess the plausibility of computationally instanced realities. Even absent definitive evidence, the methodology reinforces that investigation of simulation-like frameworks is not speculative, but adheres to empirical standards, emphasizing reproducibility, measurement, and falsifiability. Consciousness remains a central anchor throughout these considerations. Neural networks in biological systems exemplify the emergence of awareness from structured information processing. Memory, perception, and reflection arise from coordinated interactions among countless neurons, producing coherent, subjective experience. In principle, similar processes could occur in a computationally instantiated system, suggesting that consciousness is compatible with informational substrates, regardless of physical instantiation. Awareness, therefore, remains genuine and experientially consistent, whether arising in a biological brain or within a hypothetical simulated environment. Philosophical contemplation continues to enrich understanding. Reflection on the nature of reality, the coherence of observed phenomena, and the structure of consciousness provides context for human experience within a vast and intricate system. Ethical questions about the treatment of conscious entities, existential inquiries about purpose, and epistemological considerations about the limits of knowledge all arise naturally. These reflections remain grounded in observable properties of the universe and consciousness, integrating empirical understanding with conceptual insight. Finally, attention returns to the observer situated within this complex system. Every measurement, sensation, and thought occurs within a coherent framework governed by consistent rules. The universe exhibits structure, order, and emergent complexity, whether naturally evolved or computationally instantiated. Engaging with these phenomena cultivates intellectual curiosity and reflective calm, emphasizing the elegance, coherence, and subtlety of the cosmos. Awareness, observation, and comprehension unfold together, providing both insight and serenity as the mind contemplates the intricate mechanisms underlying existence itself. As our observational capacity expands, so too does the subtlety with which we can probe the universe's underlying structure. Advanced telescopes, spanning the electromagnetic spectrum from radio to gamma rays, chart the cosmos with ever-increasing precision. Surveys map the intricate web of galaxies, tracing filaments and voids that stretch across billions of light-years. Each structure conforms to gravitational and physical laws, yet the emergent complexity suggests coherent organization across vast scales. Researchers examine the distribution of matter, velocity flows of galactic clusters, and gravitational lensing to detect patterns or irregularities that might hint at deeper organizational principles, potentially consistent with an information-driven framework. Simultaneously, particle physics continues to illuminate the fundamental rules that govern these large-scale phenomena. High-energy collisions probe interactions among elementary particles, validating and refining the standard model while searching for physics beyond it. Neutrino oscillations, rare decay processes, and the behavior of quarks under extreme conditions provide precise tests of underlying symmetries and conservation laws. The regularity and predictability of these interactions reinforce the perception of a coherent, rule-governed universe. Within the context of simulation, such precise adherence to structured principles resembles the behavior of complex computational systems executing deterministic rules. Quantum mechanics further accentuates the informational nature of reality. Superposition, entanglement, and decoherence describe how systems can exist in multiple potential states until interactions necessitate a defined outcome. These principles demonstrate that outcomes are instantiated contextually, depending on observation or measurement. Analogously, computational simulations often defer detailed rendering until required, conserving resources while preserving coherence. While the universe's behavior remains fully physical and empirically testable, these analogies provide a conceptual bridge linking observation, information processing, and emergent phenomena. Cosmic fine-tuning remains a compelling feature of the observed universe. Physical constants, the gravitational constant, the fine structure constant, and others, occupy narrowly constrained ranges, allowing the formation of stars, planets, and chemistry capable of sustaining life. Small deviations in these parameters could prevent the emergence of complex structures, highlighting the delicate balance underpinning observable reality. Whether interpreted as a statistical outcome of multiverse variance or as a manifestation of underlying computational rules, fine-tuning underscores the universe's capacity to generate and sustain complexity compatible with observation and consciousness. Emergent complexity manifests most tangibly in life itself. Biological systems operate according to chemical and physical laws, yet display self-organization, adaptation, and reproduction. DNA encodes information processed by cellular machinery to produce functional organisms capable of perceiving and interacting with their environment. These processes exemplify how local interactions governed by fundamental principles can generate higher-order structures exhibiting robustness, resilience, and adaptability. In this context, life embodies the emergent properties that arise when coherent rules interact over time, producing phenomena that are both intricate and intelligible. Technological modeling parallels these natural processes. Computational simulations of molecular dynamics, stellar evolution, and galaxy formation reveal that complexity arises predictably from the application of basic principles over time. Artificial intelligence demonstrates that organized networks of information can produce emergent behavior, learning, and adaptation. These observations reinforce the notion that rule-governed interactions, whether in natural systems or computational constructs, are sufficient to produce coherent, intricate, and meaningful patterns, mirroring the observable universe's properties. Observational tests of potential underlying structures continue to evolve. Investigations of high-energy cosmic rays, gamma ray bursts, and particle behavior at extreme energies, explore the limits of Lorentz invariance, isotropy, and space-time continuity. Precise measurement of the cosmic microwave background and gravitational waves provides additional data to assess the uniformity and coherence of large-scale structure. While no anomalies definitively indicate a computational substrate, these inquiries demonstrate that empirical science can engage rigorously with the concept, producing testable predictions and refining models of fundamental physics. Consciousness remains a central thread throughout these examinations. Neural networks within the brain demonstrate how structured information processing generates awareness, memory, and perception. If consciousness is fundamentally computational, emergent systems within a simulated or informationally structured universe could, in principle, experience awareness indistinguishable from that of biological entities. This understanding emphasizes that subjective experience retains significance and authenticity even if the underlying reality operates according to informational principles rather than purely material ones. Philosophical reflection completes the narrative arc. Considering the possibility of a simulated or computationally instantiated universe prompts questions about purpose, agency, and ethics. Observers may contemplate the responsibilities of creators toward conscious entities or reflect on the nature of meaning within a structured system. These reflections remain grounded in empirical understanding of physical law, consciousness, and emergent phenomena, integrating scientific insight with philosophical inquiry to provide both intellectual depth and contemplative resonance. Ultimately, the convergence of cosmology, quantum mechanics, particle physics, biological complexity, and consciousness underscores a universe that is structured, intelligible, and capable of sustaining observers. Whether naturally emergent or computationally instantiated, the laws of physics exhibit coherence across scales, producing predictable patterns and facilitating the emergence of life and awareness. Engaging with these layers fosters curiosity, reflection, and appreciation, encouraging a deepened understanding of reality while preserving the contemplative calm that accompanies the careful observation of the cosmos. Further examination of the universe reveals the subtle interplay between fundamental laws and emergent order. Across cosmic scales, from interstellar clouds to galaxy clusters, structures form through interactions governed by gravity, electromagnetism, and quantum forces. Star formation follows predictable sequences of collapse, ignition, and fusion, creating chemical diversity that seeds planetary systems. These emergent patterns illustrate how consistent physical rules give rise to complexity over time. Each layer of structure, from microscopic interactions to vast cosmic webs, reflects coherence and predictability, demonstrating the intricate choreography that governs observable phenomena. At the microscopic level, quantum mechanics continues to elucidate the nature of information and interaction. Particles occupy superposed states until measurement, entangled systems display non-local correlations, and decoherence defines transitions from probabilistic to determinate outcomes. These behaviors, repeatedly verified experimentally, highlight that the universe operates on relational, information-dependent principles. From an informational perspective, such mechanisms can be likened to computational optimization. Only the necessary details are instantiated when interactions demand them, conserving resources while preserving overall consistency and emergent complexity. The fine-tuning of universal constants remains a striking feature. Gravitation, electromagnetic coupling, and nuclear interaction parameters exist within narrow ranges, enabling stable stars, planetary systems, and chemistry conducive to life. Minor deviations could render the universe sterile, highlighting this delicate balance underpinning observable structure. Whether these values arise through multiverse selection, natural physical law, or computational instantiation, their coherence allows emergent phenomena, including observers, to manifest reliably. This precision underscores the apparent efficiency and stability of the system, essential for sustaining complexity across scales. Life exemplifies emergent order within these frameworks. Chemical interactions governed by physical laws generate self-organizing structures capable of reproduction, adaptation, and evolution. DNA encodes information that, when expressed, produces functional organisms interacting dynamically with their environment. These emergent systems demonstrate hierarchical organization. Simple rules at lower levels give rise to complex behaviors at higher levels. From a computational analogy, the universe operates similarly, with fundamental principles producing sophisticated outcomes, enabling consciousness and perception to arise naturally within coherent systems. Technological simulations mirror these processes, providing insight into how complex structures emerge from rule-based interactions. Stellar evolution, molecular dynamics, and galactic formation models illustrate that iterative application of foundational principles generates outcomes consistent with observation. Artificial intelligence demonstrates that networks of information can produce emergent behavior, learning, and adaptation. These parallels emphasize that structured rules, whether physical or computational, are sufficient to produce coherent, intricate, and meaningful phenomena, aligning with the observable universe's properties and emergent complexity. Observational strategies continue to explore potential informational or discretized aspects of reality. High-energy cosmic rays, gravitational waves, and precision particle measurements probe the limits of isotropy, Lorentz invariance, and space-time continuity. Cosmic microwave background surveys reveal patterns of anisotropy and density fluctuations that inform models of universal structure. Although no definitive evidence of computational instantiation has emerged, these approaches exemplify the capacity of empirical science to engage rigorously with such concepts. Measurement, reproducibility, and falsifiability anchor exploration in observable reality, ensuring scientific integrity. Consciousness persists as a focal point. Neural networks within the brain integrate vast arrays of information to produce coherent perception, memory, and self-reflection. Emergent awareness arises from structured interactions, producing continuity of experience across time. In principle, similar mechanisms could operate in informationally instantiated systems, allowing awareness to manifest indistinguishably from biological consciousness. This reinforces that subjective experience retains authenticity regardless of the underlying substrate, emphasizing the intrinsic significance of perception and reflection in any coherent system. Philosophical contemplation complements these empirical and theoretical considerations. Observers may reflect on meaning, purpose, and ethical responsibility, even in a potentially simulated universe. Questions about agency, consequence, and the treatment of conscious entities emerge naturally, rooted in empirical understanding of consciousness and structure. Engaging with these questions promotes intellectual depth and reflective calm, allowing awareness to reconcile curiosity about underlying principles with acceptance of immediate experience. Thoughtful reflection enhances both comprehension and tranquility, creating a holistic engagement with reality. The multiverse hypothesis situates these insights within a broader context. Numerous universes, each with distinct physical laws and parameters, may exist, with some capable of sustaining complexity and observers. Statistical reasoning suggests that observation within a universe conducive to life is inevitable. Simulation, if present, could represent a mechanism for exploring or instantiating such universes. Observations of matter distribution, cosmic evolution, and isotropy reinforce the impression of a coherent, law-governed system, whether emergent naturally or instantiated computationally. These perspectives provide a framework for understanding the interplay of complexity, order, and observation in a potentially informational universe. Ultimately, the universe presents a tapestry of structure, coherence, and emergent complexity across all scales. From fundamental particles to conscious experience, interactions unfold according to consistent, measurable rules. Observation, reflection, and analysis reveal intricate patterns, deepening understanding and appreciation. Whether reality is naturally emergent or computationally instantiated, the laws governing it exhibit coherence and precision sufficient to support complexity, perception, and reflection. Engaging with these patterns nurtures both curiosity and calm, allowing the mind to navigate the profound architecture of existence with insight and serenity. As observations deepen, attention turns to the interplay of subtle forces shaping the cosmos. Galaxy clusters move along gravitational currents, while intergalactic gas interacts with magnetic fields and radiation, forming complex structures observable across millions of light years. Patterns of density and motion, traced through spectral analysis and redshift surveys, reveal a universe that behaves consistently, with interactions governed by measurable laws. The coherence of these structures suggests that large-scale dynamics emerge naturally from the cumulative effect of countless local interactions, producing stability without explicit guidance beyond physical law. At the quantum scale, experiments continue to uncover layers of information-driven behavior. Entangled particles maintain correlations over vast distances, demonstrating that spatial separation does not prevent consistent relational outcomes. Superposition allows systems to exist in multiple states until an interaction resolves possibilities into specific results. These phenomena follow strict mathematical rules and are reproducible, highlighting the predictable nature of outcomes even amid apparent randomness. The reliability of quantum behavior across diverse experiments reinforces the notion that fundamental interactions are inherently structured, enabling higher-order phenomena to emerge. Fine-tuned constants remain essential to the formation of complex systems. Gravitational forces dictate stellar life cycles, nuclear forces regulate fusion processes, and electromagnetic interactions enable chemical bonding. Slight variations in these parameters would disrupt planetary stability, chemical complexity, and the conditions for life. Their precise calibration ensures that matter organizes coherently, from atomic structures to galaxies. This interdependence demonstrates how small-scale laws ripple across scales, producing the conditions necessary for emergent phenomena, including observers capable of reflection and analysis. Life exemplifies organized complexity arising from simple rules. Biochemical networks convert energy, replicate, and evolve, producing structures that respond adaptively to environmental pressures. Genetic information encodes instructions that guide cellular processes, while populations of organisms adapt collectively over time. These systems show how iteration of fundamental principles produces sophisticated outcomes, revealing the mechanisms through which order arises naturally. Observing these processes highlights that complexity is not imposed externally, but emerges from the interaction of constrained variables under consistent laws. Simulations and computational models mirror these natural processes. Molecular dynamics and astrophysical simulations demonstrate that the iterative application of rules generates emergent structures consistent with observation. Artificial neural networks and machine learning systems illustrate how complex behavior arises from interconnected units following simple algorithms. These analogies provide a framework for understanding how coherence and complexity can result from structured information, reinforcing the idea that intricate phenomena need not require external intervention beyond the operational rules of the system. Empirical tests probe for subtle structural features that might indicate discretization or informational constraints. Observations of cosmic microwave background fluctuations, gravitational waves, and high-energy particle distributions allow precise mapping of underlying patterns. Researchers search for non-random correlations, anisotropies, or limits in propagation that could suggest a discretized substrate. Even absent definitive evidence of simulation, the methodology emphasizes reproducibility and falsifiability, demonstrating that potential computational aspects of reality can be approached rigorously. Consciousness remains interwoven with these considerations. Neural processing in the brain integrates information, producing perception, memory, and awareness. Emergent cognition depends on coordinated interactions across networks of neurons, yielding coherent, subjective experience. If consciousness can arise from structured information, similar emergent awareness could exist within computationally instantiated systems. Awareness remains authentic and meaningful regardless of substrate, highlighting that the experience of observation and reflection is robust, whether instantiated biologically or informationally. Philosophical reflection complements scientific exploration. Observers may consider meaning, ethical responsibility, and the implications of emergent systems. The coherence of physical law and the structured nature of conscious experience provide a foundation for thoughtful inquiry. Questions of agency, observation, and consequence arise naturally, rooted in empirical and theoretical understanding rather than speculation about intent. Reflective contemplation encourages clarity, intellectual engagement, and a measured sense of presence within the observed universe. Large-scale cosmology continues to reveal interconnected dynamics. Dark matter and dark energy influence galactic motion and the expansion of the universe. Observations of gravitational lensing, galaxy formation, and cosmic background radiation refine understanding of structure and evolution. Each measurement confirms the consistency of physical laws across time and space, providing a framework within which emergent complexity unfolds. Patterns observed at the larger scales echo those seen at microscopic levels, suggesting that coherence is maintained across orders of magnitude, supporting the emergence of life and observers. The interplay between empirical evidence, theoretical models, and reflection provides a comprehensive perspective. Interactions at quantum, chemical, biological, and cosmic scales form a continuous web of cause and effect. Complexity emerges naturally through iterative processes constrained by law. Consciousness interprets, analyzes, and reflects on these patterns, situating awareness within the broader system. Observation, measurement, and contemplation form complementary modes of engagement, allowing understanding to deepen while experience remains coherent and grounded. Attention shifts to the subtle interplay of information, energy, and structure that governs the universe at every scale. Galaxies, clusters, and filaments trace the gravitational scaffolding of matter, while cosmic radiation and high-energy particles provide a record of past interactions. Measurements of these phenomena reveal remarkable uniformity, punctuated by localized variations, illustrating how predictable laws produce both stability and diversity. Observing these interactions emphasizes that complexity emerges as a consequence of consistent rules applied over time, allowing coherent patterns to manifest across vast scales. At the subatomic level, quantum behavior continues to reveal the information-driven nature of interactions. Particles exhibit discrete energy states, interference patterns, and entanglement correlations, all of which are reliably described by mathematical frameworks. Experimental results consistently confirm that the universe's behavior is governed by predictable, probabilistic rules. These patterns suggest that emergent phenomena, from atomic structures to chemical reactions, are not random but arise from structured principles capable of generating coherent complexity. The formation of stars and planetary systems exemplifies this emergent order. Gravity condenses interstellar clouds into protostars, initiating nuclear fusion that synthesizes heavier elements. Planetary bodies form from residual material, following orbital dynamics that yield stable configurations. These processes, constrained by physical laws, produce environments capable of sustaining chemical diversity and, eventually, life. The consistency and predictability of these outcomes demonstrate that large-scale complexity naturally arises from fundamental interactions, reinforcing the idea that organized systems are inherent to the universe's structure. Life represents the next level of emergent organization. Molecular networks self-assemble, cells replicate, and organisms evolve, producing adaptive behaviors and environmental interactions. Genetic information guides these processes, resulting in systems capable of perceiving, processing, and responding to stimuli. This hierarchy of emergence illustrates how simple rules, applied iteratively, give rise to increasingly sophisticated phenomena. Observation of these processes reveals that coherence and functional complexity can emerge from interactions governed strictly by physical law. Technological analogies provide insight into how structured interactions generate complex outcomes. Computational models simulate molecular behavior, astrophysical dynamics, and neural networks, demonstrating that iterative rules produce patterns indistinguishable from those observed in nature. Artificial intelligence exhibits emergent learning and adaptation, reinforcing the principle that organized systems can generate sophisticated outcomes without external intervention. These parallels underscore that the universe's emergent complexity is consistent with both natural and information-driven frameworks. Empirical investigations probe the potential limits and structure of reality. High-energy physics experiments test fundamental symmetries, particle behavior, and space-time properties. Observations of the cosmic microwave background and gravitational waves provide a detailed map of universal structure. Anomalies or correlations within these datasets offer opportunities to examine whether the underlying substrate exhibits discrete or computational characteristics. While no conclusive evidence has emerged, the scientific rigor applied ensures that investigation remains rooted in observation and reproducibility. Consciousness continues to integrate with these observations. Neural processes generate awareness, memory, and perception, illustrating how structured interactions produce subjective experience. The emergence of self-reflection, reasoning, and observation within these systems highlights that consciousness itself is a coherent outcome of rule-governed interactions. If informational substrates can support similar emergent processes, awareness remains authentic and continuous, underscoring the intrinsic value of observation regardless of underlying instantiation. Philosophical reflection frames these insights. Observers consider meaning, ethical responsibility, and the implications of structured, emergent systems. Questions of agency, consequence, and perception arise naturally, grounded in empirical understanding and logical reasoning. Awareness and reflection allow for a measured engagement with reality, blending observation with contemplation. Thoughtful consideration enhances understanding while fostering a sense of calm, encouraging the mind to navigate complexity with equanimity. Observations of large-scale cosmology provide additional context. Dark matter, dark energy, and gravitational interactions shape galactic motion and cosmic expansion. Measurements across multiple scales confirm the consistency of physical laws, enabling emergent complexity to unfold predictably. Patterns of density, motion, and radiation trace coherent processes that extend from microscopic interactions to galactic networks, illustrating continuity of law and order. These observations reinforce the perspective that complexity, awareness, and emergent phenomena are naturally compatible with a structured universe. As reflection deepens, attention rests on the experience of observation itself. Every interaction, measurement, and thought occurs within an intelligible system of consistent principles. Consciousness perceives and interprets patterns, situating awareness within a coherent framework that spans particles, stars, and galaxies. The interdependence of emergent phenomena across scales, combined with reliable physical law, fosters both comprehension and a sense of quiet. Observation and understanding unfold together, revealing the intricacy and elegance of a universe capable of producing order, complexity, and reflection simultaneously. The universe reveals its patterns not only in vast cosmic structures, but in the interplay of information and energy that governs every interaction. Galaxies rotate, stars ignite and fade, and planets orbit predictably, demonstrating the consistent application of fundamental forces. These dynamics, observable and measurable, create environments where chemical complexity can emerge and sustain processes capable of supporting life. Each layer of interaction, from atomic particles to planetary systems, exhibits coherence, highlighting how organized behavior arises naturally from underlying principles. At the smallest scales, quantum phenomena continue to illustrate the structured behavior of reality. Particles occupy discrete energy states. Interactions follow precise mathematical rules, and entangled systems maintain correlations over distance and time. These behaviors, confirmed repeatedly in laboratory experiments, show that even probabilistic systems operate under consistent principles, allowing emergent complexity to be reliable and predictable. The patterns observed reinforce the idea that fundamental laws provide a framework for the emergence of coherent structures across scales. Emergent complexity is evident in life itself. Biological systems self-organize, adapt, and evolve, producing networks capable of perceiving, responding to, and altering their environments. DNA encodes instructions that guide development, reproduction, and interaction, demonstrating how information is translated into functional outcomes. These processes reveal how hierarchical organization arises naturally. Simple rules at the molecular level give rise to sophisticated structures at higher levels, culminating in consciousness capable of observation and reflection. Consciousness integrates these observations, interpreting and making sense of patterns across scales. Neural networks process information, generating awareness, memory, and decision-making. The emergence of subjective experience illustrates how complex behavior arises from the structured interplay of simpler elements. Whether consciousness exists within biological systems or could theoretically emerge within informational substrates, its coherence and authenticity remain intact, demonstrating the universality of structured information as a foundation for awareness. Observational science continues to refine understanding of the universe's organization. Measurements of cosmic radiation, gravitational phenomena, and high-energy particle behavior reveal patterns consistent with stable, rule-governed dynamics. Surveys of galaxy distribution, stellar evolution, and planetary formation provide further evidence of emergent order. Even subtle anomalies are examined rigorously, emphasizing the capacity of empirical investigation to probe the boundaries of known physics, while remaining firmly grounded in observation and reproducibility. Reflection on these patterns encourages both intellectual and contemplative engagement. Awareness of coherence across scales, from quantum interactions to cosmic structures, fosters understanding and quiet appreciation. Ethical and philosophical considerations emerge naturally, inviting thought on the implications of consciousness, agency, and observation. These reflections are grounded in empirical understanding and logical reasoning, allowing the mind to reconcile curiosity with a sense of calm presence within a structured, intelligible universe. Patterns of large-scale cosmology, emergent complexity, and consciousness converge into a coherent picture. The universe exhibits order and regularity, enabling life, perception, and reflection to emerge naturally. Structures from the microscopic to the cosmic maintain consistency, and processes follow predictable interactions that allow sophisticated phenomena to manifest. Observation and comprehension reveal the elegance of this system, highlighting the subtle interconnections between fundamental law, emergent behavior, and conscious experience. In the quiet awareness of this intricate universe, one can appreciate the coherence of patterns, the reliability of natural law, and the emergence of complexity without external imposition. Every star, particle, and thought is part of an unfolding system, interrelated and intelligible. Conscious observation allows recognition of this interconnectedness, fostering calm reflection and understanding. The mind can rest within this framework, perceiving the elegance of structured interactions and the subtlety with which complexity and awareness emerge together.